So welcome everyone. This is the next presentation of the Internet Ecosystem and Evolution subject. And today we are going to discuss one of the most important constituents of the Internet, namely the IP routers. So we're going to deal with IP router architectures, and we're going to look into one of the most important and most interesting theoretical and practical questions related to IP router design, and this is the fib lookup algorithms. Namely how to implement longest prefix matching. The idea here is that so far we've dealt with the large-scale structure of the Internet. So basically we modeled each autonomous system as a single node, regardless of the fact whether the said autonomous system is basically just something which constitutes a couple of routers and end hosts, or it is a large-scale tier 1 autonomous system with possibly thousands of routers and middle boxes and hundreds of thousands of hosts, regardless of the size, regardless of the importance in the internet, regardless of the location or the importance of an autonomous system in the internet transit hierarchy. We just modeled each autonomous system as a single node. And then we looked at the internet large-scale structure that arises as the interconnection of these autonomous system nodes with transit and peer links, and we asked questions related to how this autonomous system level large-scale structure of the internet looks like, and what kind of routes emerge on top of this autonomous level system view of the internet. In this lecture we are going to jump, we make a huge jump from this large-scale model where we basically abstracted away the fine scale structure of the internet and the individual hosts and routers and middle boxes that make up the network to a small scale view where we are just going to look into these constituents and basically the most important network devices that make up autonomous systems and that make up the internet, and these are IP routers. So IP routers are becoming important when when we depart from our autonomous system level, our high level view of the internet, and when we start to look into the microstructure of networks and autonomous systems and the like. So we are going to discuss what an actual IP router is, some of the most important facts about IP router architectures and IP router design, and then, as I mentioned earlier, in the second part of this lecture, we're going to discuss one of the most important and most difficult problems related to IP router design and implementation. And this is the problem of the longest prefix matching lookup, namely how to implement longest prefix matching in an efficient and fast way. But first, let's just jump to some basic facts about IP router architectures and IP router design. So what's an actual IP router? This little excerpt is from Wikipedia, which basically says the router is a networking device that forwards data packets between computer networks. So basically a router is connected to a couple of IP networks, and then one data comes in from one of these attached IP networks. Then the router reads the network address information in the packet header, and then using information in its routing table or its routing policy, it basically just directs the packet to the next network along its end-to-end path. Okay, so this is the basic problem that IP routers solve. In a little bit more detail, if you look a little bit further, then we're going to see that most of the routers that make up the internet is the two type of network components, which are organized into separate processing planes structurally or architecturally. So the control plane, it basically contains all the functionalities that are required in a router to maintain the routing table or the forwarding table that we've used so far, that lists when a route should be used to forward a data packet. So this is basically about maintaining the fib, the forwarding information base that is used by the underlying data plane or the forwarding plane of the router, which basically takes the information in this fib, in this forwarding table, and then forwards actual data packets between incoming and outgoing interface connections based on the information that is stored in the fib by the control plane. If you take a functional view at the data plane design, we're going to see that the IP packet forwarding on the surface is a rather simple task. This is basically just the following 4 steps that the router needs to repeat for each and every packet that it receives from one of its interfaces. So suppose that a packet comes in. It's basically an Ethernet frame. It first it's being processed by the link layer in the protocol stack, which is basically the lowest layer in the protocol stack. Let it be, for instance, Ethernet. The Ethernet layer processes the packet, the MAC layer, and then if this is an IP packet, then the Ethernet layer uses the Ether type in the Ethernet frame header to identify IP, say IPv4 or IPv6 as the next protocol for which the payload of the Ethernet frame has to be passed on, and this is the point where the task of IP packet forwarding comes in. This is usually implemented by the IP router engine that is designed into the IP router. So these are the 4 important steps that we make from this point. The first is IP header check. So this is a standard checklist that we need to just check in order to validate an incoming packet. We need to check the format of the packet, whether it conforms to the IP standards, the version information in the IP header, the header length options, and we need to recompute the header checksum to check that the IP header just came through Ethernet intact without any actual bit errors in it, which would immediately invalidate the information that is contained in the IP header. So this is the first step, is the IP header check. This is a standardized list of checking of things that we have to check regarding the IP packet format. The second step is the fib lookup. So we need to parse out the destination address from the IP packet header, and then we must find the most specific fib entry for this destination IP address in the packet, because this will give us the outgoing interface and the next hop IP address on which we need to pass this packet on towards this destination. We're going to look into fib lookup with a very, very fine detail in the second part of this lecture. The third step is TTL handling. So recall that TTL is the time to live field in the IP header is used to preclude packets from that may enter into intermittent loops, routing loops in the network, to circulate in these loops forever. So the idea is that we have the TTL field, which keeps on being decreased or decremented by the IP routers along which the packet passes. It eventually reaches 0 when it goes into a loop, and then when the TTL reaches 0, then we drop the packet. And this makes it possible to remove packets from routing loops without actually killing the network by these packets that would keep on circulating there forever. So this is the third step of IP packet forwarding, and the last step is to recompute the header checksum. So this is an interesting step. Why we need that? Recall that the TTL itself is part of the IP header, and the header checksum actually just protects the bits in the IP header, all the bits in the IP header, against actual bit errors. So when the TTL changes, the header checksum also changes, and we need to recompute it for each and every packet. But this is, despite of the fact that this looks like a very complex task to do, most of the time this can be very efficiently implemented in hardware or with special tricks. There are also a couple of optional steps that we may do with special IP packets, like handling fragmentation, IP options, etc. We are not going to look into that in too much detail. So IP routers range, basically just range on a very, very broad spectrum. So starting from these simple devices that we have installed in our homes, which basically IP routers that provide access to the IP hosts that we have in our household, like tablets and laptops and smart TVs and things like that, and this connects these IP devices to the rest of the network. These are low-end IP routers, all the way up to these high-performance routers, which are in this example, one is from Cisco, and the other is Juniper, which provide gigabits or hundreds of gigabits or even terabits of packet per second performance, and consumes huge amount of power. So in this spectrum, ranging from the low-end routers all the way up to these high-performance routers, we have all sorts of different products which essentially can be used in different contexts, in different scenarios and different conditions to fit the particular purpose, the particular speed requirements, or of particular energy consumption requirements for the actual use case. Here is the usual access core edge separation applied to routers. So this is the router categorizations from RFC 4098. We've seen the access core edge separation basically encompasses all these areas of basically everything related to networking. And wherever we have a network, be that a cloud network, the internet, an autonomous system, or anything else, we usually have this access core edge separation. In this particular case, the access router is basically just a router device which can connect a huge number of subscribers, be that mobile or fixed subscribers, to the internet. So this is usually just this concentrates traffic from the internet edge to the internet core. We also have edge routers, which usually are very smart routers that run BGP in order to exchange routing information with neighboring autonomous systems. And between the access routers and the edge routers, we have the core routers, which are very high performance routers that provide reachability between different POPs, point of presences of an internet service provider. Another categorization is based on the type of the platform that the router is actually implemented in. Based on this, we have soft routers or software routers. These are basically IP routers implemented in software that run on general purpose CPUs and general purpose operating systems. Basically, the Quagga image that we use in GNS3 during the labs, this is basically a software router. It's an actual operating system, the Linux operating system, which implements the IP protocol stack and the forwarding plane or the data plane of our software router, and the Quagga daemon, which is a collection of routing protocol implementations that run on top of this operating system and provide the control plane of our software routers. Okay, these usually software routers are smaller performance devices, so these fit for smaller performance ISPs, BGP monitors, but we are now seeing a proliferation of software routers in the cloud, because basically all the virtual machines that are instantiated on a single server in a cloud need to have an IP router, a virtual IP router implemented at the server that provides access to these virtual machines from the rest of the internet and from the rest of the cloud network. So we are now seeing lots of soft routers implemented in different areas. The other important router category of router types is hardware routers. These are typically high performance routers which use special purpose hardware devices. I'd like to call the attention to this actual abbreviation, which is the abbreviation for application specific integrated circuits. So usually router vendors design their very specialized hardware chips that are used only for processing IP packets, and then build router architectures around these ASICs, which end up being very high performance hardware routers for edge and core routers in large ISPs. And usually this is also the design that we use in access routers when we have maybe tens of, maybe hundreds of thousands of subscribers that we need to provide access to the internet. This is the general IP router architecture when we are dealing with hardware routers. In software, we have something which is very close to this, but the hardware architecture is maybe something which is still more relevant today. The three most important constituents are the control card, which runs basically the control plane of the router, and in the data plane we have line cards, which basically just provide very low-level access to the one or more IP ports and IP interfaces to disconnect these IP interfaces to the router, and the interconnects which connect the line cards and the control CPU into just one router. So in the data plane we have line cards, one or more line cards and an interconnect, and in the control plane we have the control card. Let's look a little bit more into this, each of these important constituents. So the control card basically runs the router logic. So the intelligence of the router is implemented there. What belongs to the intelligence? Basically everything that is very difficult to implement in hardware. The control card runs the routing protocols like BGP or OSPF. It provides management access, so runs the command line interface, similar to the terminal emulator that we are using in the labs, the VTYSH utility. All routers have this sort of command line interface access to the routers, but we also have simple network management access, simple network management protocol access to the routers, which allow to manage the router remotely. We have all these different monitoring and extra services that are also implemented in the control cards, and it basically manages the interconnect and sets the FIB information in the line cards whenever we need that. Usually the control card itself is a general purpose PC, so we have a general purpose CPU like an x86 Intel architecture, gigabytes of RAM. So most of the time we even have a general purpose OS, operating systems running on these control cards, which is most of the time, or it is being more, Linux is being used more and more in this context, but different router vendors have their own operating system that run on the control card. Let's jump from the control plane to the data plane. The most important component of the data plane is the interface card or the line card. This provides basic packet input-output functions. Usually the line card has one or more physical ports or interfaces that allow different IP networks and different links to be attached to the router. These are the serial, fast Ethernet, gigabit Ethernet, and things like that. These are the standard Cisco names for the different types of technologies that we might use in these different links. And then the line card, say a high-end line card would implement, say, 8 Ethernet, gigabit Ethernet ports, and provide the basic functionality to interface this simple physical port with the rest of the router. It's usually implemented in a special purpose hardware, which might be a network processing unit, which is a dedicated CPU-like architecture for running network processing tasks, or it might be an actual hardware chip that is designed just for this purpose and just for this line of routers. So this is the hardware processing element that provides basic header parsing and processing functions, and we also have fast static memory. So in spite of the control CPU, where we have DRAMs, which are usually much larger, much cheaper, and much slower, in the line card we have static RAMs, which are very fast, but usually very expensive and much smaller scale than DRAMs. Okay, most routers allow extension with new line cards. So this allows us to scale up a router from a couple of line cards. Say we want to increase the capacity of a router, so basically just purchase a couple of new line cards from our router vendor, and we just push this into the rack of the router, and then we can immediately start to use these line cards, maybe even in a hot upgrade, and start to attach or just plug in new Ethernet interfaces along these line cards. And the last component is the interconnect or the black plane. So this is essentially just a switching matrix. It provides communication between the line cards and the control CPU, and a couple of low-level buffering functionalities. So whenever there is contention for accessing, say, a line card or a line card port, then the backplane provides a simple buffering architecture to allow the accesses to be queued. There are lots of ways to design interconnects. This can be a shared bus or internet switch. Some of the high-end routers today use a separate Ethernet switch and a separate Ethernet network to implement the interconnect itself. There are lots of interesting design and architectural questions related to the implementation of the interconnect with the backplane, but we are not going to look into this any further. Instead, we are turning our attention to two very important definitions or concepts related to the hardware design of IP routers, and this is the fast pass and the slow pass. Okay, the fast pass is basically the steps of packet forwarding that are being implemented inside the data plane. Okay, so whenever a packet comes in, and processing the packet can happen entirely in the data plane without the control CPU being involved in any way, we say that this packet is being processed on the fast pass. This basically means that we have all the functionalities available at the ASIC to parse the packet all the way up to the IP layer, and we have all the information necessary in the SRAM, like maybe the entire forwarding information base, to be able to for us to be able to select the actual line card and the actual Ethernet port along which we have to pass this packet on. So wherever this is the case, our router is sufficiently intelligent and advanced to implement all these necessary functionalities, all the 4 steps of IP packet forwarding in the line cards. Then the packet does not need to reach out to the control CPU, and in this case we have a line rate performance achieved for forwarding these types of packets. So whenever we look at the datasheet of an IP router, we usually see these gigabits or terabits of seconds per performance, but this is mostly relates to the fast pass operations. So whenever everything goes in the data pass, then the router can reach its theoretical maximum performance. In contrast, we also have slow pass processing in IP routers. This means that we don't have enough information and we don't have enough intelligence or processing capability implemented in the data plane of our routers to be able to forward or process an IP packet. We need to invoke the control CPU and the general purpose operating system and the IP protocol stack of our operating system to process the packet, and that way we need to reach out to the control CPU. The problem is that this particular interface between the data plane and the control plane, this usually starts to act as a bottleneck in these types of slow pass operations. So usually it's a very, very expensive task to pass packets from the data plane to the control plane and then back again the processed packets. This way, the slow pass packet forwarding can be orders of magnitude slower than fast pass packet forwarding. So, what are the types of operations that we need the control plane to be involved in? These are usually the complex operations that are very difficult or cannot really efficiently be implemented in hardware. There are a couple of examples, real-world examples for when a packet takes a recourse into the control card. One is the processing of IP options. Recall that in IP we can include additional optional IP options in the IP header, which add additional behavior to the processing of our IP packet. And wherever we have these types of IP options, these usually cannot be implemented, cannot be parsed in the line card. So whenever the line card detects that there is an IP option in the IP header, it just blindly sends the packet onto the control CPU, where we can process these very complex IP options from software. The other is might be fragmentation. Some of the line cards do not have enough intelligence to be able to implement all the fragmentation and defragmentation state machine of IPs. So whenever an IP router detects fragments, it may involve the control CPU and the slow-pass processing. Protocol message handling. So whenever we get a BGP packet, of course we need to pass this on to the control CPU, because the control CPU is the actual place where we run the BGP daemon. ARP, ICMP packet generation. These are all types of different functions that may or may not be implemented on the fastpass. Now, depending on the price tag and of course the sophistication of our router, we have more and more functionality implemented in the data plane, and we have more and more functionality, or more and more types of processing operations that can be implemented fully in the data plane on the fastpass without the control plane being involved. But of course, these types of routers, which have all the intelligence in the line cards to say provide IP options processing, these are usually much more expensive and of course much faster than low-end routers. Let's look a little bit into the high-level view of how IP routers architectures evolved during the last 40 years. In the first generation routers had only just very simple functionality implemented in the line cards. It's basically just a MAC layer. Recall that the MAC layer, the minimum access control layer, is basically the Ethernet stack. So basically, the line cards themselves could only process Ethernet headers, but nothing else. So wherever we had an IP packet, the first generation routers just sent these packets to the CPU. The IP protocol engine was implemented in the CPU, and then CPU was the one that assigned the outgoing interface for these IP packets. So in a first generation router, every packet goes through the slow pass. Of course, there was the strong push to implement more and more functionality, to move more and more functionality from this fully fledged IP stack to the line cards proper. So we started to see different basic IP processing functions to be implemented on the line cards. So we have the second generation routers, where a simple input queue and the FIB cache appeared on the line cards. What is a FIB cache? It's basically just a simple storage that provides caching for the IP address or the FIB lookup information for the last couple of packets that the line card received. So whenever we have a packet, a new packet for which we don't have information in the FIB cache on how to forward this packet, we just send this packet on to the control CPU. The control CPU, of course, assigns the outgoing interface, and it also updates the FIB cache with the new routing information. So whenever other packets, so new packets of the same flow will be received on this line card, we have all the information available in the FIB cache to be able to process those packets fully in the data plane on the slow pass, on the fast pass. So in second generation routers, we have this nice luxury that whenever a packet finds its destination address in the FIB cache, we have fast pass forwarding. Otherwise, we have to go to the slow pass. The last router generation that we consider here is third generation IP routers. Here the full FIB is downloaded into the line card. Of course, we have much more advanced and much higher capability line cards to support in these third generation router architectures. So we have all the FIBs implemented in the line card. So we have all the functionality and all the information available in the line card to process normal IP packets fully in the fast pass, and only for very complex operations like IP options or fragmentation, things like that, we have to go to the slow pass. Okay, so wherever we have normal packet processing, these third generation routers provide full fast pass operations. Of course, for this, we need the CPU to constantly update the line card fibs. And since there can be tens of or dozens of line cards installed in a single IP router, this can be a very tedious task. A couple of notes about the programmable data plane, because this is the new sort of, I would say, fourth generation IP router architecture that we are now witnessing in the industry. So these conventional black box routers that we've talked so far is basically just come from the vendors with all the data plane and the control plane operations fixed and built in, and we have no way to actually to say tweak the BGP implementation in our IP router, or just deploy or introduce new types of protocols in this protocol processing in these routers. Now for different use cases like cloud or 5G or IoT or private WANs, this architecture is just too rigid. So for instance, Google will want its own special protocols to be implemented by routers, so they cannot rely on Cisco providing them all the implementations for these custom protocols that they want to deploy. This basically pushed vendors towards so-called white box switches, where basically the data plane and the control plane is separated by a well-defined interface, and the functionality implemented in the data plane can be fully reconfigured from the header formats and protocols all the way to match action tables and processing rules and the packet processing steps and their orders. So the control plane has all the liberty to maybe implement completely new protocol processing and deploy these on the fly without actually any need to, say, reboot the router or anything else. So the programmable data plane and software-defined networking seems to be the future in router design, and we are now witnessing a large-scale movement from a couple of providers like 5G provider networks and cloud and IoT providers to just move to these programmable data plane designs. But still, at the moment, most of the routers that we see out there, these high-performance routers, follow this third generation design.